For most of human history, progress followed a predictable pattern. Tools became faster, stronger, more efficient, but they always played by the same fundamental rules. Computers followed that pattern too. Every leap forward still relied on the same binary logic, ones and zeros, on and off, true and false. Quantum computing breaks that pattern entirely. In late 2024, inside a highly controlled research facility in the United States, a quantum processor was briefly activated for an experimental run. The device itself was physically unremarkable, small, delicate, and requiring extreme environmental conditions to function at all. Yet during a short operational window, it completed a computational task that highlighted a growing divide between what classical machines can simulate and what quantum systems can directly perform. The significance of that moment was not speed alone. It was what the results suggested about computation itself. To understand why, we need to step back and examine the difference between classical and quantum machines, not at a marketing level, but at a physical one. Classical computers process information using bits. Every calculation, no matter how complex, reduces to a sequence of binary decisions. Even the world's fastest supercomputers, systems that occupy entire buildings and consume enormous amounts of power, never escape that limitation. Quantum processors operate on a different foundation. Their basic units, known as quantum bits, behave according to the laws of quantum mechanics. Under controlled conditions, these units can exist in multiple states simultaneously, a property that has been repeatedly verified through laboratory experiments. When multiple quantum bits interact, their states can become correlated in ways that cannot be described independently. This is not speculative language. These effects are measured, engineered, and actively used. However, quantum computing has long faced a severe obstacle: instability. Quantum states are extremely fragile. Minute disturbances, thermal fluctuations, electromagnetic noise, or environmental interference can destroy the very properties that enable quantum computation. For years, this fragility imposed a practical ceiling. Early quantum systems could demonstrate quantum behavior briefly, but scaling them introduced overwhelming error rates. Adding more components made calculations less reliable, not more. That limitation shaped the field for decades. Progress began when researchers shifted strategy. Instead of attempting perfect isolation, they designed architectures where quantum elements actively stabilize one another. In these systems, individual units continuously monitor neighboring units, allowing errors to be detected and corrected indirectly without collapsing the entire system. This approach led to a counterintuitive outcome. Larger systems could become more stable than smaller ones. During the late 2024 experiment, the processor was assigned a benchmark task commonly used to evaluate quantum advantage, a test designed to exploit quantum correlations in ways that classical machines cannot efficiently reproduce. From a validation perspective, the outcome aligned closely with theoretical expectations. Error rates fell within predicted bounds. Statistical distributions matched models derived from established quantum theory. But deeper analysis revealed something that warranted closer attention. Post-run diagnostics showed residual correlations persisting slightly longer than standard models would anticipate. These effects were subtle, not dramatic failures or obvious violations, but they were consistent enough to raise questions among researchers reviewing the data. It is important to be precise here. No confirmed breakdown of known physical laws was observed. The results did not prove the existence of alternate universes, hidden dimensions, or unknown intelligences. What they indicated was behavior occurring at the boundary of current theoretical frameworks, a region where multiple interpretations remain mathematically valid. One interpretation, discussed in physics for decades, treats quantum events as branching outcomes rather than singular ones. Under this framework, quantum systems evolve across many possible states simultaneously, with measurement selecting only one observable outcome. Historically, this interpretation was viewed as philosophical rather than practical. It produced the same experimental predictions as other interpretations and offered no testable distinctions. Quantum computing changes that context. When machines operate in regimes that classical systems cannot simulate, even in principle, interpretation becomes unavoidable. Researchers are forced to confront what the mathematics actually implies about physical reality. Some physicists argue that quantum computational advantages can be explained entirely within conventional frameworks, without invoking branching realities. Others suggest that the mathematical structure naturally supports parallel evolution of states beyond classical intuition. At present, there is no experimental consensus. The data supports multiple explanations equally well. Following the experiment, the processor was taken offline for calibration and analysis. Publicly, this was described as standard procedure. Quantum systems require frequent recalibration, and shutdowns between major runs are routine. What drew attention was not the shutdown itself, but the measured pace of disclosure that followed. Data releases were partial. Follow-up experiments were delayed. Collaborations shifted focus from performance metrics to foundational interpretation. This shift is unusual but not unprecedented. When experimental results operate at the edge of theoretical understanding, interpretation becomes as important as engineering. The broader implications extend far beyond any single device. Quantum mechanics already challenges intuitive notions of time, causality, and locality at microscopic scales. What changes with large-scale quantum computation is visibility. These effects no longer remain confined to isolated laboratory demonstrations. They begin producing functional, measurable outcomes. This raises deeper questions. What is information? Is it merely something processed by physical systems? Or is it a fundamental ingredient of reality itself? Some theoretical frameworks suggest that space, time, and matter may emerge from underlying informational structures rather than the other way around. If this is true, then quantum computers are not just faster calculators. They are instruments capable of interacting with reality at a foundational level. Despite the attention surrounding this experiment, quantum computing remains in an early developmental phase. Current systems are fragile, resource-intensive, and limited in scope. Their practical applications are still constrained. History, however, offers perspective. Early aircraft were unstable and impractical. Early electronic computers were massive and inefficient. Their importance lay not in immediate usefulness, but in what they demonstrated was possible. Future quantum systems may revolutionize chemistry, materials science, logistics, and cryptography. They may also force revisions in how physics understands computation, time, and causality. None of this requires sensationalism. It requires patience, rigor, and careful interpretation. The most important conclusion is not that reality has been breached, but that technology has advanced to a point where foundational physics questions can no longer be ignored. We are no longer asking whether quantum mechanics works. We are building machines that depend on it, and those machines are beginning to expose how incomplete our understanding remains. The experiment did not answer the deepest questions about existence, but it clarified something essential. The next phase of discovery will not come solely from looking farther into the universe, but from probing the rules that govern it. This is not the end of the story. It is the opening chapter.